All right, today we're going to unpack one of the most fundamental processes in all of chemistry. It's something that connects the slow, kind of beautiful aging of a city landmark with the raw, explosive power of a rocket launch. We're talking about oxidation-reduction reactions.
So to get started, just take a look at these two images. On the left, you've got this historic building with that really distinct green coating. It's called a patina. And on the right, well, you have the incredible power of a rocket taking off. They seem like they're from totally different worlds, don't they?
But what if I told you that they're both powered by the exact same type of chemical process? That's really our big question for today. What on earth could these two things possibly have in common?
The answer, it's a chemical story. It's a tale of two reactions that are always, and I mean always, happening together. And they're shaping the world all around us in ways that are both super quiet and incredibly explosive.
This whole process is called an oxidation-reduction reaction, or if you want to sound like a chemist, you just call it a redox reaction. And when you boil it all down, it's about one simple thing, the transfer of tiny particles called electrons between two different things.
So let's break that down a little. In every single redox reaction, you've got a giver and a taker. It's this fundamental exchange. You could almost think of it as a little battle for electrons.
And this reaction is always split into two parts that have to happen at the same time. Oxidation, that's when something loses electrons, and its partner, reduction, that's when something else gains those exact same electrons. You can't have one without the other. One loses, the other gains. They're a total package deal.
Okay, that all sounds pretty straightforward, right? But there's a catch. Electrons are absolutely tiny, subatomic. We can't actually see them jumping from one atom to another. So, how in the world do chemists keep track of this invisible exchange?
Well, this is where it gets pretty clever. Chemists came up with a brilliant solution, a system that I like to call electron accounting. It's basically a set of rules that lets us track where the electrons are before a reaction and where they end up after. And the main tool in this accounting kit is the oxidation number. Just think of it like a bookkeeping number that we assign to an atom. Now, it's not always a real physical charge, but it's an amazing tool that lets us see if an atom has gained or lost electrons during a reaction.
Let's start with what has to be the easiest rule in the book. Key rule number 1, the zero rule.
And this rule is just beautifully simple. Any pure, uncombined element, we're talking about a pure chunk of sodium metal or the oxygen gas in a tank, it has an oxidation number of 0. That's it. It's our neutral, balanced starting point. Okay, next up is key rule number 2, the charge rule. And you know what? It's just as straightforward. The rule is pretty much exactly what it sounds like. If you have a simple ion, just one atom with a charge, its oxidation number is simply its charge. So for a chloride ion, which has a charge of -1, its oxidation number is, yep, you guessed it, -1. Easy.
So what happens with neutral compounds? This is where it all comes together. For any neutral compound, the sum of all the oxidation numbers has to add up to 0. Take a look here at calcium carbonate. Now, we know from other rules that calcium is a +2, and oxygen is a -2. But wait, there are 3 oxygen atoms, so that's a total of -6 from them. For the whole thing to add up to 0, that carbon atom in the middle must have an oxidation number of +4 to balance it all out. See? It's like a little puzzle.
All right. Now that we have our electron accounting tools, our little detective kit, we can finally go back to our original mystery and play chemical detective. It is time to crack the case of the green patina. Using what we've just figured out, we can understand exactly what's happening, chemically, on the surface of that copper roof. So here's the big reveal. Over a long, long time, the copper metal is oxidized, and the oxygen from the air all around it is reduced. It's a slow, steady redox reaction that's happening right out in the open.
Let's just break that down one more time. First, the copper atoms on the roof, which start with an oxidation number of 0, lose their electrons. That's oxidation. At the exact same time, oxygen atoms from the air swoop in and gain those electrons. That's reduction. And that invisible transfer is what creates that beautiful and actually protective green layer. Mystery solved.
But here's the thing. This is so much bigger than just one building or even one rocket. Once you know what to look for, you start to realize that our entire world, in so many ways, runs on redox.
And I mean, it's truly everywhere. You see rust forming on a car? That's just iron being oxidized. The battery that's powering whatever device you're watching this on right now, that's just a very carefully controlled redox reaction. There are even skunk spray remedies that use redox to neutralize the smell. And, maybe most important of all, the process your own body is using to get energy from your food, cellular respiration, that is just a beautiful, incredibly complex series of redox reactions.
So that brings me to one last thought. Now that you can see this fundamental pattern, this giving and taking of electrons all around us, it really makes you wonder, what other invisible reactions are shaping your world right at this very moment?